All right. So we did the case where the velocity is constant, so it makes sense that now we'll do the case where the velocity isn't constant. And that's called acceleration. So since velocity is a vector, there are a couple ways that we can say an object accelerates. So this is where the definition in physics is different than what you might think. So whenever you hear accelerate, you're always thinking of the speed up, usually, right? When your car accelerates, you're getting faster. That's actually only one of three ways to accelerate. You can accelerate by speeding up, by slowing down, or by changing direction, right? Because the velocity arrow could get longer, the velocity arrow could get shorter, or the velocity arrow could spin, right? Those are all ways of creating different arrows. So just be wary of that. Although we're really going to focus on the first, just speed up or slow down case for now. We'll deal with the direction change later with circular motion. So we define the acceleration very similarly to how velocity is defined, where it's this rate of change, except we're taking the rate of change of the velocity instead of the displacement. So this is just another rate. And you might have noticed that velocity itself is a rate. So this is a rate of a rate, or a second rate, or a second derivative for the calculus people out there. Additionally, whenever we have a quantity that changes over time, we'll give a subscript of a 0 for the initial value, and we usually just don't label its current value. So that's why we do that. So this is really just the v change over the time change. Now, units of acceleration are weird for some people to think about initially. Now, if we just work this out directly, the top would have units of meters per second, and the bottom would have units of seconds. These do not cancel, right? Because first of all, why would acceleration be meters? But it's just not, that's not how fractions work. So this actually has a really nice meaning in this form. Acceleration tells you how many meters per second your velocity is gaining or losing every second in the 1D case. But just to simplify this, because it's kind of ugly to look at, we will write this in the equivalent form. Remember, we can keep change flip this, right? Meters per second times 1 over second, which is meters per second squared. Now, this is good for a different reason. This communicates that it's sort of a second rate, right? Because speed is the first rate, so acceleration is the rate of the rate, which is why we have an exponent of 2 here. And just like with average velocity, it's just an average, although usually we'll pick cases where acceleration is constant. That's like the most common case of motion in this class, constant acceleration. But if there is an average acceleration that's not equal to the instantaneous, keep shrinking your interval, right? We want to go deeper and deeper and deeper and deeper until your delta t is like infinitesimally small. Then it would be a perfect estimate of the instantaneous. Oh, what a surprise. The pullback car is back. So we have the following dot diagram. As we did last time, dots are spaced by 0.1 seconds. So again, this is like a 10 FPS camera where we're just going click, 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 showing where the car is every frame. This is 0 seconds, this is 0 0.1, 0 0.2, 0 0.3, 0 0.4. So, is the car speeding up, slowing down, constant speed? Justify your answer using the dot diagram. Well, remember, these are equally spaced in time. So this really tells you, the gaps are telling you how far the car went in that frame. So the car is speeding up because the adjacent dots are increasing their spacing relative to the last interval, telling you you have gone further this frame than last frame. So d over t increases for the interval. All right, now let's read the ruler. Let's check our values here. So this is 1 centimeter, 2, 3 centimeter, 4, 5, 6, 6 centimeters, 7, 8, 9, 10 centimeters, 11, 12, 13, 14, 15. So those are my positions, 1, 3, 6, 10, 15. Now, we can actually tell from the table, although I think that's a question later, so I'll save it. You can actually tell from the table itself this is speeding up by looking at gaps. Let's sketch a graph of position. We do have a grid, so accuracy matters here. So we said it was 1, 3, 5, 6, 10, 15. No, 1, 3, 6. 1, 3, 6, 10, 15. Oh, it's a line. Do not just draw a line. We have no reason to believe this is linear. Now, if you actually wanted to sketch the shape this makes, it's a curve like this. But do not just draw a random line, especially, like, you can maybe convince me we might need a line if this point wasn't here. But this is definitely not a line. Don't just draw a random line, please. So let's try to find each of the following. Speed of the car at 0.1 seconds versus the speed of the car at 0.3 seconds, and then the average acceleration. So we have a choice here. We have to figure out, where should I take my speed between, try to get a good estimate of the speed at that time. So notice I don't have the exact speed at 0.1 seconds, so I have to estimate it. So how I would do that is I would look for anywhere where 0.1 is in the middle of. So for example, 0.1 seconds is in the middle of 0 and 0.2 seconds. So what I would do is I would say that V of 0.1 is approximately equal to the average on 0 and 0.2, right? Because 0.1 is in the middle. So I would just take the change in position over the change in time on that interval. So this is just really taking the slope of the data points. So for example, between 0 and 0.2, I have displaced 3 centimeters, and that took me 0.2 seconds. So this would be, oh, much too complicated for me using the calculator. Ooh, 15 centimeters per second. I would not have guessed. So just to pause and talk about what I did here, is I don't have the actual speed at 0.1 seconds. So I just guessed that if I take the average speed between 0 and 0.2, 0.1 is in the middle of that. So it's probably a good estimate. Now I'm just going to do some copy pasting and do the same idea for t equals 0.3 seconds, except I'm just going to make some changes. So 0.3 is probably a good estimate of whatever is happening between 0.2 and 0.4, right? So I just do the same thing. So between 0.2 and 0.4, at 0.4 I was at 10, at 0.2 I was at 3, and same idea. Notice this is definitely like a slope looking calculation. And typing this in, oh, who knows what this is, 35. Huh, that's definitely bigger, right? That should make sense. If we are speeding up, we should definitely have an average speed that's getting bigger with time as we shrink these intervals, right? The 0.1 estimate is definitely going to be lower than the 0.3. All right, let's calculate the average acceleration using this. So acceleration is defined as delta V over delta T. And we're just estimating. So we're estimating that the final speed was 35 centimeters per second. The starting speed we're estimating was 15 centimeters per second. And the change in time was 0.1, sorry, 0.3 minus 0.1 seconds. Can I do this in my head? Probably, but I don't trust myself. So I'm getting 100 centimeters per second, or 100 centimeters per second squared if we reduce the. So what this says is that every single second, I don't go 100 centimeters, right? Because I'm going different speeds. So I don't go the same centimeters every second. This tells me how many centimeters per second of speed, 100, I am getting every second. So let's make sure that all these things are consistent with speeding up. How is the table consistent with speeding up? Well, notice that the time intervals are the same. This second, I went 1 centimeter. This second, I went 2 centimeters. This second, I went 3 centimeters, then 4, then 5. So this is really just the gaps, right? So every gap is getting larger. So I would say the differences between adjacent positions are increasing. So why is that justification? Well, this means the d of each time interval is increasing, which means the speed is also increasing because you're covering more distance in the same time interval. What about the position time graph? We didn't really talk about this. Look at this shape. Well, first of all, it's not linear. So we know it can't be constant speed. So we see that this curves upward. We have a special name for this, which we'll talk about later, called concave up. But what this means is that we see that the slope gets steeper. Why does that matter? Well, that means that rise over run, which is the speed, is also increasing. Right? More d in the same t. That's what the slope is saying, right? See how it's getting steeper and steeper and steeper. How could we modify the dot diagram to make the accuracy better? Well, I've said this a couple times, so I hope that this is clear because it's this idea of how can we make this estimate, right? How can we make this better? Well, the key is just increase the FPS of your camera, right? So instead of going click, tenth of a second, click, tenth of a second, click, why not bump up the FPS? So shrink delta T, right? That's the key here is your approximations become better uh, as you shrink that time interval. All right, slightly different version now. We have the table first. So hopefully we can speed this up kind of using what we gained from kind of looked at every representation here. As they come up, I've been introducing these. This is closest to what's called like a translation between representations or a TBR, where we show you all the different ways to visualize a problem. Usually it involves some pictures, some math, some graphs, and consistency checks. All right, speeding up, slowing down, constant speed. Well, we said we could determine it from the table below by looking at gaps, right? So this is plus 18. This is plus, no, nope, can't do it. 14. This is plus 10. This is plus 6. This is plus 2. And defeated by adding by 14. Do it. So, what does this tell us? Well, this actually tells us, because this is sort of the gap length on a dot diagram, this says we'd get a dot diagram that looks like this. And this is the mirror image of the speeding up dot diagram. So, of course, this is slowing down. This is slowing down because gaps are decreasing. Let's estimate the speed by doing that average technique, where if you take the speed on an interval that's close, you can estimate the speed in the middle. All right, well, we already have these nice gaps for us. So notice that t equals 1 is smack dab in the middle of this one. T equals 3 is smack dab in the middle of this one, and this one, and this one, and this one. So if we just do a bunch of d over t's for these intervals, we can get a pretty good estimate, at least hopefully. So uh, so for here, we're looking from 0 to 2. Here, we're looking for 2 to 4, 4 to 6, 6 to 8, 8 to 10. So we're just doing the slope on these intervals. So let's see. So on my first second, or my first 2 second interval, I went 18 meters. So this is 18 over 2. My second interval, I went 14, then I went 10, then I went 6, and then I went 2. So again, I'm dividing all the gap lengths by 2 because it was 2 seconds per gap, right? You went 18 meters in 2 seconds. So you get that speed. So just doing the division here, which I am capable of, we get 9, 7, 5, 3, 1. Let's do some sketches of the position and estimated velocity. Now, position we can do exactly. Oh boy, you're really gonna make me graph this. And by you, I mean me. Stupid. I have to estimate where 18 is. That's like just shy of 20. Then I'm at 32, 42, 48, and 50. So we can see here, this is not an upward curve, but it's sort of curving down. We see it's getting shallower, showing that slowdown. And then what about V? Well, this one I can do, right? Because we're just going at the odd numbers. 9, 7, 5, 3, 1. And this actually does look like a straight line. So using your graph from part C, calculate the acceleration of the object. Well, we know that A is equal to delta V over delta T, which would be the slope of a velocity graph. So we can just rise over run this. We don't want to go all the way down, right? It doesn't. So notice that I go, what is this? Oh, we'll just do it by hand. 1 minus 9 meters per second divided by 9 minus 1 seconds, which is negative 8 over 8. So negative 1 meter per second squared. And this should actually be clear from the data that it's negative 1, right? Because notice that every 2 seconds, my velocity goes down by 2 meters per second. So I'm losing 1 meter per second. All right, are your graphs from part C consistent with one another? Justify your answer. Well, if we did everything right, the answer should be yes to these questions. So we see that the slopes of x are decreasing. So since v equals the slope of x of t, this must mean that v should therefore decrease. Thus, the graphs are consistent. So in other words, notice that our graph is getting shallower, which means that our speeds are decreasing. And if I look at my speeds are definitely going down. So everything matches here. So another TBR check there. All right, simple math time. Velocity of object with a speed VO is shown. We're going to show a bunch of different ways it can accelerate. Here are our final velocities. We just want to show the delta V in each case. All right, well, notice that in scenario 1, I'm going from a speed of VO every time. In scenario 1, I just end with 2 VO. Well, if I start from a right arrow and end with a longer right arrow, I just needed to add a little right arrow to it. Scenario 2, I'm actually ending upwards. So not only did I need to cancel the original velocity, I also needed to add the new upward arrow. So we actually get a diagonal one for scenario 2. For scenario 3, it's the same idea except negative. And then scenario 4, how do I go from right to 0? Well, I just a single left. So let's actually calculate the magnitude of the velocity change in each scenario. So scenario 1, that's pretty straightforward, because my velocity just changed by adding v0 in the I hat direction. So there's no Pythagorean theorem or any weirdness happening here. It's just v0. Now for scenario 2, delta v equals, well, I had to do a leftward velocity VO, and I had to add some upward velocity VO. So for this one, it's actually going to be a Pythagorean theorem situation, where this is v0 and this is also v0, and we want to find this quantity here. Now here's another common thing we will see when dealing with trig. There's a special right triangle, right? Because its legs are the same. Now we could just do this, right? So I get 2 copies of v0 squared under the square root, so this would just be root 2 v0. This is a common thing to know, right? If your right triangle legs are the same, the hypotenuse is just root 2 times one of the legs. And then scenario 3 is going to be almost the same by symmetry. It's just instead of adding left and up, you're adding left and down. It is the same triangle though, so we're just going to skip to the root 2. And then scenario 4, well, this is the stopping case, so we just add the v0 left. So let's rank the magnitude of the acceleration in each scenario. It does tell us that these velocities are achieved after the same time. So acceleration is just delta v over delta t magnitude wise. So we're just ranking this numerator because the denominator is the same. So we have a two-way tie, 1 and 4. And then we have another two-way tie. This is kind of a tricky one compared to what we were doing before. Anytime we get symbols, it can be trickier. So this change was v0. Well, this acceleration would be v0 over delta t. This change would be root 2 v0 over delta t. I didn't ask you to justify. All right, we'll conclude with another special case. I said that one of the most common motions we will model in this class is constant acceleration, and here's a special case of constant acceleration, which is where basically anytime you throw an object or drop an object, you'll assume that there is no air resistance. So anytime you toss an object or drop an object on Earth, there will be a constant downward acceleration due to Earth's gravity, which we denote as little g. Precise value is 9.81 meters per second squared on Earth. So this is about our special planet. But we will always round this to 10. I am a g equals 10 purist because I love my clean numbers. I don't know how to count by 9.8, but I can definitely count by tens. So I will round everything to 10, and I encourage you to. AP encourages you to. It really helps with conceptual understanding to use 10. Now, if you're doing labs, you might argue 9.8 is more accurate, but I might argue you're worse at measuring than you think. 9.8 versus 10 probably doesn't matter in your experiment. Assuming you're doing a physics lab and not like making air. Please use the actual G. So using this model, all objects will hit the ground regardless of their shape because we assume there's no air resistance. Now, you can watch the classic, it's probably the BBC of them pumping out a huge missile silo or something where it's a vacuum and they drop a feather and bowling ball and it's the same because there's no air. So this all the hitting the ground at the same time thing that happens when there's no air. So just realize that this is a model. Free fall model. Now, what is it good for? It's good for dropping things like spheres. Like most things will hit the ground at the same time if they're just solid shapes. You have enough intuition to probably know the types of things that make air resistance not negligible. Like obviously a bowling ball and a piece of paper won't hit the ground at the same time. But a metal sphere and a wooden sphere probably will in the So how do we count by G's? Well, again, this tells you that every second you fall, you gain this velocity. So you add this every second. So every second, add 10 meters per second down. So what this means is that if you're falling, your speeds are going to increase 10, 20, 30, 40, 50. But if you toss an object up, the up and down are going to cancel. So this is shown by this dot diagram here, right? If I toss an object up, gravity is going to slow it down by 10 on the way up, eventually stops it, then it speeds it up on the way down. Now, this can be like purely vertical motion, but just to avoid clutter, because there's some symmetry here, we like to spread out the dot diagram when it's free fall, just to make it more clear what's happening, and because it helps when we deal with throwing things well. So our rule is that every second you add 10 meters per second down when there's a falling object or All right. Object is tossed up with a vertical speed of 30 meters per second. Assuming dots are spaced by 1 second, draw the vertical acceleration of the ball at each position. Well, acceleration is just g, which is 10 meters per second squared downward. So you are 10 meters per second squared. You are 10 meters per second squared. Yes, even at the top. Why? Well, G is caused by Earth's gravity. Does Earth's gravity just shut off because you're at the top of your trajectory? No, I didn't think so. Now, what's the vertical velocity of the ball at each position? Well, this, we know it starts out at 30. What happens 1 second later? Well, I add 10 meters per second down. 30 up, 10 down, net result 20 up. Add 10 again, but it's 10 down, so that makes 10 meters per second. You could also think about it as adding negative 10, right? 30 minus 10, minus 10, minus 10, minus 10, minus 10. So now you can see why they're adding on the way down, right? Because you're just getting more negative. So nice symmetry here. Ball spends 6 seconds in the air. How could you figure this out without the dot diagram? Well, it's pretty clear it's 6 from here, right? Because it says here 1, 2, 3, 4, 5, 6. I could just count the dots. But we don't have that luxury all the time, and I'm trying to get you to think about this conceptually. So notice that there's some nice symmetry here. So because we start at 30, I'm just asking, how many times do I have to count by 10 to stop? Well, 1, 2, 3 times of counting by 10, I stop. And then due to symmetry, what goes up must come down, and that's just reflected. So this is how I stated this when I typed it up. So if the ball is launched upwards at 30 meters per second, it takes 3 seconds to stop because I need 3 copies of 10 to stop the 30. And then you just double it by symmetry. So now we're going to test our knowledge just by doing the 3 cases of free fall, where we have dropped, thrown down, and thrown up. All right, object A is dropped from a tall cliff at t equals 0. Calculate the speed of the object at 4 seconds. How long does it take to get that speed? Yes, I did choose that intentionally. You should be glad that's the only sort of relevant pop culture-y things I try to do with this. As much as I'm sure that you would love to have all my objects replaced with tung 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 sahur. Try to limit my brain rot in this and try to make these at least somewhat professional. All right, speed of object A at 4 seconds while we drop it. So I think it's easier just to like think about it. So I drop it. And 1 second later, it'll be moving at 10 meters per second. 2 seconds later, it'll be moving at 20 meters per second. 3 seconds later, it'll be moving at 30 meters per second, and so on. So we can see that if we're just dropping the object, it's just going to gain 10, 20, 30, 40, 50, 60, etc. So this is just going to be 40 meters per second. Now, when will the object have a speed of 67 meters per second? Well, this is where I think making a table helps. So here's the same thing kind of in just table format where we dropped it from rest, so there's no initial velocity. And every second, we're sort of gaining 10 meters per second of downward velocity. So we can see that it is definitely going to be not 6 seconds, right? Because that would be 60 down, not 7 seconds, that would be 70 down. And then we can just think about the fact that it's linear. So 7 is 7/10 of the way between 60 and 70, so it is just going to be 6.7 seconds. Now, how did I figure that out, or how could you use 9.8 for this? Well, all I did is just 67 divided by 10, right? How many times do I have to add 10 to get to 67? Now we have a different case where I toss it downward from a tall cliff at t equals 0. So this would be I throw it downwards at t equals 0. So this would be a speed of -5. And g doesn't care what your velocity started as. It's still going to add -10 every second, right? So notice it's still that sort of increase by 10 in the negative direction thing. We just have like a different initial value or y-intercept. After 1 second, we see it is just going to be 15 meters per second. And when will it reach 100 meters per second? Well, we could set up an equation here. Well, we got to get to 100. We know that our starting speed was 5, and we gain 10 every second. So we can see we get 95 equals 10t, so t equals 9.5 seconds. So I'm trying to avoid using like a lot of official equations we will learn for this in the next sections, just to get us thinking about linearity. There are formulas that we will do these questions a lot more efficiently with in the future. Just trying to get us to think conceptually. All right, and then the last case is we toss the object vertically upwards at 25 meters per second at t equals 0. So going up at 25, so gravity will be slowing this object down initially. So add negative 10, add negative 10, add negative 10, add negative 10, and so on. So when will object C momentarily stop? Well, this is that idea of the previous question where we said how many copies of 10 are needed to stop the velocity when it started at 30? Well, it was 3. We can see the answer is definitely going to be between 2 and 3 seconds here, right? Because it went from positive to negative. So we are just asking here, it is just 25 divided by 10, which is equal to 2.5 seconds. When will object C return to the ground? Well, by symmetry, the uptime is equal to the downtime. So T is just 2 times 2.5, which is 5 seconds. And then defining a velocity upward as positive, sketch a graph of each velocity. So this would be, this is the dropped object. This is the tossed down object. This is the tossed up object. So tossed down, dropped is easy, right? I just drop it and it's always moving down. G is a constant acceleration, so that's going to be nice and linear. I don't want that. I'm just going to. Wait, no, we got this. The slope would be negative 10. Now, if I toss it downwards, it's the same graph. It's just going to have a y-intercept, negative. And then tossing up an object, same idea. I'm just changing the y-intercept again. And I think it's worth noting explicitly here that the slope is equal to negative 10 meters per second squared in all of these cases. Oh, come on, I just want the slope. So this is a bit conceptual. Like, it's okay if this was a bit challenging, this last part. We will find formulas that do this stuff for us, but I thought it was interesting to approach this just using the idea of acceleration for. So that is how we deal with modeling accelerated motion.